listed for you under each of the remaining 3 series, the sequence of terms and the sequence of partial sums. So if you want to go ahead and pause and just double check that you have the same thing I have. I just want to be sure that everybody is kind of aware of the difference between these. And so the sequence of partial sums is something that's accumulating as you go. Okay, what I want to do now is finish up by just quickly showing you the graphical interpretation of what's happening here. So we talked about the fact that to get from say the 5th partial sum to the 6th partial sum, right? The 5th partial sum is what you get when you add up the first 5 terms in the series. The 6th partial sum, you add up the first 6 terms. So to get from the 5th to the 6th partial sum, you would just add the 6th term of the series to the 5th. So that has a really nice graphical interpretation, and I just want to go over there. I apologize, I hadn't pasted this in here yet in my notes, the Desmos link, so I'm just going to go to it, but in the handout that you've downloaded, I have put in the link here for this Desmos worksheet. So we'll go over here, and in this Desmos worksheet, I've just put in for the harmonic series, that's the series where we're summing up 1 over k, where k goes from 1 up on up. And so I've graphed in black the sequence of terms. And so you can see here when there's this table that has, as x ranges from 1 to 10, then you have the first column here is 1 over x going from 1 to 10. So it starts out here at 1, then 1/2, then 1/3, and so on. And then in the next column, we have the partial sums. So the first partial sum is just the sum of the first term, so it's just 1. And then the second partial sum is 1 plus 1/2. So we have 1.5 here. So you can see where that is here. I guess I can actually here highlight the points that I'm talking about. So to get up to this red point that I've highlighted, the difference from 1,1 to 1.5, that vertical distance is the same as the height of the black point here, 1/2, right? So we've added that black height to 1,1 here to get the height of this next partial sum in the red set of points. And the same thing goes here if we're going from the second partial sum to the third partial sum, right? How much have we added? What's that vertical distance between those 2 points? Well, it is exactly the height of that third term in the series. So the third black X here. And so on. So you can see that what's happening is we're taking the heights from the black X's and we are stacking them up successively to get these red dots here. And so that's really the graphical picture that I want you to have in mind. Let me go ahead and just put a little sketch of that in here. So, oops. Okay, so we'll change colors back here. So graphically, right, okay, so what do we have here? We have we can represent our sequence of terms. So suppose this is B1 here. So there's 1, maybe, and maybe I will just make this axis less cluttered. I'll go ahead and label this a different way. So I'll have B1, B2, B3, and so on. And then out here, we'll put B N. Okay, and maybe we'll just make Bn at that height. So let me adjust this a little bit here. This is not Bn, this is the number n, and this height here is B sub n. Okay, so now let's think about our sequence of partial sums. So the partial sums then, I will go ahead and I'll draw those in red. So B1, and then I'm going to go ahead here. That's the same as S1. And then we're going to add B2 to S1. So this is kind of nice. I can just copy and paste and get another copy of this. Oops. Maybe not. So I can grab this and I can move it. I'm attempting to do this, but it's not. All right, so I won't waste any more time here on that. What I want to say is that we can come over here and we can move up from, this line shouldn't be here, we can move up from S1 by exactly this amount here. And so we end up with, whoops. Okay, I'm not doing well with the stylus here. All right, let's delete. All right, sorry for these technical difficulties. So here's what I'm trying to do here is indicate that we go up by the same amount here to get to S2. And then to get to S3, well, we want to increase by this amount. So there's S3, right? So S3 is now B1 plus B2 plus B3, and so on. And so if we have, in fact, so if I have n minus 1 out here and I somehow know what Sn minus 1 is, then to get to Sn, right, all I'm doing is adding here, this distance is Bn. So I hope you can see that right here in my my little sketch. So that's the relationship, and let me label this here. This is Sn, the nth partial sum. So what I just want you to see the relationship between the sequence of terms, so in other words, these blue dots here that we want to be adding up, and the sequence of partial sums, which are where we've added up the first set number of terms. Okay, so you'll have access to this Desmos worksheet. So next we want to talk about convergence. And so I have a different Desmos worksheet here to kind of go back to what we did with the geometric series. And so again, this other Desmos worksheet is actually going to have the modification made because in a geometric series, we're thinking about starting at 0 here. And so so this other Desmos worksheet has that going on. So we'll just go ahead and open this series there. And you can see that here, so I've used the function 3 times 1/2 to the x, right? So I'm looking at the series A is equal to 3 and r is equal to 1/2. And what we said when we started looking at whether a geometric series converged or not, we said that we would look at summing up the first, say, 10 elements of the series, see what that sum is, and then we would make that number larger. So we would say, well, if I sum up the first 20 elements of the series and the first 30 elements of the series, do I start to approach some value? And we said that the value you might approach is what we would call the sum of the series. And so, of course, you know from our work with geometric series that this does converge, right? And so here I can just hit enter, and I can continue this list down, and you can see that in fact in my list here I am approaching 6, right? And of course we know if you go back through and calculate the limit of this series, you'd find that it actually indeed is 6. And you can see here the orange terms, right? Those are the terms 3 times 1/2 to the n, and then the black are the partial sums of that series. Notice here that these are starting at 0. So we actually have plotted something right here at n equals 0. And of course, at n equals 0, the partial sum and the term is the same because it's the first term of the series, right? And I guess in this particular case, right, we also are starting our summation here at 0. So you'll see things lining up like that. So here we conjecture then that this series does converge, and we even worked out in algebraically that in fact whenever r is less than 1 in absolute value, then this any geometric series will converge. So let's go ahead and go back to our notes, and we'll just I'll just record what we had from that demo. So our example was for a equals 3, r equals 1/2, and the partial sums, well, we decided that that the limit as n goes to infinity of the partial sums as n looks to be 6. And in fact, we calculated that. That was the calculation that we did in the last section. So maybe I will just say one thing that I guess I should mention here is that the SNs that I plotted on the previous page, because of starting at 0, there's a little bit of a difference with what the usage of SN. So, but graphically, that's the picture that you want to have in mind. So, okay, and let's go ahead and I'll just point out that if we were to take a equals 3 and r equals, say, 1.1, then the limit as n goes to infinity of Sn does not exist. And you can see that here. We'll just quickly come back, and if I go up here and change this from 1/2 to 1.1, right, then you can see, right, that the orange terms start increasing, and of course the black terms are also shooting off, and this can be as, say, I can even come down here 0.99, right, and if I have 0.99, theoretically we know that this should be increasing right? Sorry, increasing. We know that this should be increasing, but that it will level off at some point. And so we just haven't graphed far enough to see these partial sums leveling off towards their limit. So I think that was one thing I would say is a little bit of a limitation here with these graphical investigations, is that you do kind of have to know how far to graph in order to see the limiting behavior. And we're going to see that it's actually, for some cases where the convergence is slow or the divergence is slow, this is a way we can get some intuition, but it's not a way of proving that a series converges. So, okay, so with that said, I'd like you to be able to use this as a tool, but not rely on it as a crutch. So let's go back to the notes here. And so the idea is that this graphical interpretation here kind of informs how we define whether a series converges. So let's go ahead and get the formal definition of convergence here. So we will say that the series converges if and only if the nth partial sum, this sequence of partial sums converge. So IFF just means if and only if, so it converges if and only if the sequence of partial sums converges. And so in other words, this converges if the limit as n goes to infinity of the sum k equals 1 to n if this converges if this limit exists. Okay, and note that this is what we called here Sn. Okay, and if it exists, it must actually be some number, right? And so that value is the infinite, well, how we would define the infinite sum. So we'll also say that if the series does not converge, then it diverges. Okay, so there's our definition, and it's really just extending what we did with geometric series here. So what I'd like for you to do is to go ahead and modify the Desmos code to graph the terms of each of these series. Go ahead and put a little sketch of your modified of your graphs in, just kind of indicating what you saw when you graphed, and maybe label it with how far out you went in terms of n, or I guess k here. You could label those indices. So how far you went out on the x-axis, and then make a conjecture for each of these 4 series. And when we come back, we'll move on to how you can verify your conjectures.